guys, welcome to video 5.2.1 where we're going to be talking about titrations in just a little bit more detail. So a titration is a quantitative analysis, quantitative of course meaning numbers, in which a solution of known concentration, your titrant, is known. So if you're thinking about our past titration of potassium permanganate with hydrogen peroxide that we did, the titrant, the known concentration, was the potassium permanganate. Is added to a solution of unknown concentration called the analyte. In our case, that was the H2O2, until the reaction is complete, which is a stoichiometric equivalence point. We've just called that the equivalence point before. Often at which an indicator changes color. That's the experimental endpoint. So when you see the indicator change color, that's your experimental endpoint. And ours was a light pink. Okay, so example 1. Propanoic acid was titrated with 0.1 molar sodium hydroxide solution. So in experiment 1, you've added 25 mils of 0.1 molar sodium hydroxide, and that was needed to get to the endpoint for your propanoic acid. So it was needed to titrate 40 mils of propanoic acid to its endpoint. What's the concentration of this original solution? So here you have the milliliters and you have molar for sodium hydroxide. Here you only have the volume, so we're going to go ahead and try to find the molarity. So this whole process of going to the equivalence point is just stoichiometry. So first thing I'm going to do is just go ahead and write our reaction so we can see what's happening here. So propanoic acid, and you don't need to memorize this, this will be given to you, plus sodium hydroxide. We don't care about the sodiums, it's a spectator ion. So we're writing our net ionic, and that's going to go to C3H5O2 minus. Okay, so this whole thing of going to the equivalence point is going to be stoichiometry. So if we have 25 milliliters of our sodium hydroxide, so I'm going to go ahead and convert and get the moles of sodium hydroxide first. So I know my molarity is 0.100 mole NaOH over 1,000 milliliters. My milliliters cancel out. And then we know that it takes 1 mole of NaOH to neutralize every 1 mole of acid. So I'm going to go ahead and use my mole ratio here. So 1 mole NaOH, or just OH minus, same thing, for every 1 mole of propanoic acid. When you plug that into your calculator, you should get that you have 0.0025 moles of propanoic acid, HC3H5O2. So now we know how many moles were in our original solution. But we need to figure out molarity, which is in moles per liter. So molarity is a concentration, so I'm just going to write our brackets. Molarity of HC3H5O2 equals moles per liter. So here's my moles. So 0.0025 moles over liters. Now you don't want to use the liters of the whole solution here. You don't want to use 25 plus 40 because you don't want to know what the molarity was in the final solution. You just want to know the molarity of the propanoic acid before you started titrating it. So you're only going to use the 40 milliliters here. So 0.040 liters. Take a second and plug that into your calculator. And you should get 0.063 molar of propanoic acid as your final answer for experiment A. Or sorry, example 1, part A. Now let's take a look at part B. So for this one, try to write pretty small because there's a lot to do here and not a lot of space. So experiment 2, suppose you have a 60 ml sample now of 0.15 molar propanoic acid. How many mils of 0.1 molar sodium hydroxide is going to be needed to titrate to its equivalence point and its halfway point? So let's tackle that part first, just the first part. So the first part of this, going to our equivalence point, is again stoichiometry. So we know that we have a 60 ml sample of 0.15 molar propanoic acid. So I can convert to the moles of propanoic acid, and from that I can get moles per liter of, or I can get liters of my NaOH. So let's go ahead and do that. So I have 60 milliliters of my propanoic acid times 0.15 moles of my propanoic acid per 1,000 milliliters. There's our concentration. I know from the reaction that I wrote just up above here that it's 1-to-1 ratio. Or 1 mole NaOH or OH minus for every 1 mole HC3H5O2. And then I have my molarity of my propanoic acid here. I'm sorry, I have my molarity of my NaOH, 0.1 molar NaOH. So I'm going to plug that in to get the volume, because it's asking me how much NaOH am I going to use. So for every 1,000 milliliters, 0.100 mole OH minus. I'm using OH minus and NaOH interchangeably because for our purposes in the net ionic they're the same. We can just ignore that sodium. Okay, and so when you plug this in, you should get 90 milliliters of NaOH to equivalence point. And then to the halfway point, well, we're only going to need half of that. And so we're going to need 45 milliliters NaOH to halfway point. Okay, so that answers our first two questions here. Then, what is the pH of the solution at its equivalence point and at its halfway point? The easiest one to tackle is the halfway point, because we know at the halfway point the pH is equal to the pKa. And so, at halfway point, and we know this from our previous lesson, so that means pH is going to be equal to, and the pKa again is the negative log of the Ka, which is equal to the negative log of our Ka, oh, that's right here, negative log of 1.3 times 10 to the negative 5. Go ahead and plug that into your calculator. And you should get 4.89. And so the pH then is just 4.89 at the halfway point. Okay, last thing we need to do. What is the pH of the solution at its equivalence point? Well, at its equivalence point, we've added enough sodium hydroxide to neutralize all of the acid. And now the only thing that we have left would be the base. So we've added enough sodium hydroxide to neutralize exactly all of this acid. And then now we only have this conjugate base left, our product. So this now turns into an equilibrium type problem. So we're going to need to use our ICE table, and we're going to need to use the Kb. We're going to need to use the Kb because this is the conjugate base, not an acid. So let's go ahead and do that. So the first thing I need to do is calculate my concentration of my base, or of my conjugate base. So, at equivalence point, there's only C3H5O2 minus left in solution. So first I'm going to go ahead and figure out the moles that I have of this. So moles of our acid equals, well, I have 60 milliliters of it, and I have my molarity, so I'm going to multiply by my molarity, and I'm going to do this so I can get my volume, or my number of moles here. And so I know I have 9.0 times 10 to the negative 3 moles. Now, I know that I have 9.0 times 10 to the negative 3 moles of my acid that I started with. Since these dissociate at a 1-to-1 ratio, we can say that we also have the same number of moles of your base, right? So you have 9.0 times 10 to the negative 3 moles of acid, and then now once it's all dissociated, you have 9.0 times 10 to the negative 3 moles of your conjugate base, because it all came from this acid. So I have my moles, but now I need to figure out my volume. So molarity is moles per liter, so the concentration, C3H5O2 minus, is going to be in moles per liter. Well, I have my moles from here, 9.0 times 10 to the negative 3 moles. And I have my volume. My volume here is going to be my 1.5 liters, or sorry, 0.15 liters, because I need my total volume of my solution at this point. And since I started with 60 milliliters of the sample, and then I had to add 90 milliliters of NaOH, my total volume now is 150 milliliters. So 60 plus 90 is 150 milliliters, so that's the same as 0.5 liters. That's where I got this total volume number from. All right, plug this into your calculator, and you get that this concentration is 0.06 molar. Okay, 0.06 molar. So now I'm going to draw my ice table. I'm just going to do this in a different color, so this is getting kind of messy, so we can keep this separate. So now I'm going to go ahead and write my equation. Now my equation is going to be just for the reaction or the dissociation of your conjugate base in water in your solution, because this is the only thing you have left is your conjugate base. You're going to make a little acid out of it, but the conjugate base is the only thing you have, so it's not going to be the exact same equation you had above. So we're going to go ahead and start with our conjugate base, C3H5O2 minus, and that's going to be in water. This is an equilibrium because it's a weak base. And what does it form? Well, it's going to take a hydrogen from the H2O, attach it to itself, form the acid form of itself, propanoic acid, plus hydroxide, which is the leftover water. Now the water, that's liquid, so we don't need to include it. Initial, change, ending. And this is going to be molar concentrations. So this really essentially is just a weak base problem at this point. So we're starting with 0.06 molar of our weak base. And we're, of course, not including our water here. And our propanoic acid, we haven't made any yet. Minus X plus X plus X. It's just 1 to 1. So 0.06 minus X, X, and X. Okay, and we said before that we need to use the K expression. But here, we can't use Ka because this isn't an acid dissociating. This is a base dissociating. And so we need to use the Kb. We have the Ka, and from the Ka we can find our Kb. Because remember, Kw equals Ka times Kb. And that equation, again, is on your periodic table. So I'm going to rearrange this to get Kb equals Kw over Ka. Just going ahead and plugging that in. Kw is 1.0 times 10 to the negative 14. Our Ka was, let's see, where was that? 1.3 times 10 to the negative 5. And when you plug this into your calculator, you should get that the Kb equals 7.7 times 10 to the negative 10. So that's our Kb. So now that we have our Kb, we can go ahead and write our expression, our equilibrium constant expression. So Kb is equal to products over reactants. So you have your acid times your hydroxide here over the reactant, C3H5O2 minus. And looking at our ice table, I see that's going to be x squared over 0.06 minus x. But I'm going to ignore that minus x, remember, because it's going to be very, very small in comparison to 0.06. So Kb is equal to x squared over 0.06. And our Kb was equal to 7.7 times 10 to the negative 10. Multiply these together, take the square root to get your final answer, and you get that, I'm going to write this really small, x equals, now x is equal to the concentration of hydroxide, that's what x is, and that number, the number that you got from your calculator there, should be 6.8 times 10 to the negative 6 molar. And of course, from our hydroxide ion concentration, we can get the pOH. We can't get the pH directly, but we can take the negative log of this. So we can get pOH equal to 5.17. And from that, your pH is 8.83. Because remember, 14 minus 5.17, 8.83. And so your pH at your equivalence point is 8.83. Okay, let's look at your next problem here. This is asking us to sketch a graph of everything that we just calculated. So we're going to sketch our titration graph. We're going to describe the major species at 4 of these points, starting halfway equivalence, and then past the equivalence point, and see what's present there. Okay, so when we first started out, the pH was about 2. And then at the halfway point required adding 45 milliliters of our NaOH. And then when we calculated our pH, back up here, at the halfway point, after we added 45 milliliters of our NaOH, we see that our pH is 4.89, almost 5. So graphing that, 45 milliliters, and then we're going to go to almost 5 right about here or so. Our equivalence point required us to add 90 milliliters of sodium hydroxide. And when we added 90 milliliters, we calculated our pH to be 8.83, almost 9. So 90 is about here. pH of about 9 is right about there, a little lower. And we're going to go ahead and sketch our titration curve from these points. So the curve always goes up, kind of flattens a bit, and then goes up, and then really sharply increases right here. Now we didn't calculate the end, but we're going to estimate right about there. And so we have this really sharp increase here, and we have this really flat region here. So what are all these points? Let's label them. This is our starting point. In the middle here, this is our halfway point. And this is our equivalence point. Okay, so what are the species that are present here? Well, at the starting point, we only have the acid. So the only thing that's present here is just HA. Oh, sorry, this is a little unclear. HA. So we just have our acid present at the beginning. At the halfway point's a little bit different. At the halfway point, we have both HA and A minus. So we have both the acid and the conjugate base, or the base and the conjugate acid, depending on what you're titrating. So at the halfway point, I'm just going to write it up here. The concentration of HA is equal to the concentration of A minus. So the concentration of the acid is equal to the concentration of the conjugate base because you've titrated half of it. Another way we can write this is as a fraction. So if these are equal to each other and you divide them by one another, they're going to be 1. So the ratio of products of a reactants, HA, is going to be equal to 1. At your equivalence point, you've used up all of your acid, and now the only thing that's going to be left in solution is your concentration of your conjugate base, or the opposite of whatever you were titrating. Now, the region that we're really interested in here is this region, this flat area. This is called the buffer region. So this is the buffer region. And this is where a buffer exists, in this nice flat zone here. So in that buffer region, the ratio of products over reactants, A minus over HA here, is going to be less than 1, going this way, and the ratio of products over reactants is going to be greater than 1, going this way. But this whole region here, this is our buffer region. So at this point, if you added a little bit of acid, for example, your pH would go down, but not that much. If you added a little bit of base, your pH would go up, but not that much, until you completely use up your buffer. If you completely use up your buffer, then your pH shoots up like this. So you do have a finite amount of buffer that you've created here in this buffer region that you can use up by neutralizing with base or acid, depending on what your buffer is made out of. And then you'll shoot way up in pH at the equivalence point. And then, of course, past the equivalence point, you just keep getting higher and higher in pH. Okay, so notice that in a buffer solution, we resist our changes in pH here. Since the pH of the solution in the buffer region remains relatively flat, as an acid or a base is added to it. So the pH stays roughly the same. The very best buffer that you can make exists right here at the halfway point, because that means you can add acid or you can add base, and you can add either one and you have the most distance to go. You have the most buffer left to use up before you run out of buffer. So we're going to write that down. Notice that a buffer solution resists change in pH. And that's since the pH of the solution in the buffer region remains relatively stable. Okay, it remains relatively stable as acid or base is added to it. Takeaway here, the best or the ideal buffer takes place at the halfway point. Okay, part 3. Suppose instead of 60 milliliters above, suppose now we titrated more. We had 100 milliliters of the same concentration solution, titrated with the sodium hydroxide instead. Would the solution at the halfway point be a more or less effective buffer? Well, because we started with more milliliters, and we have more moles as a result of our acid, this is going to be a better buffer, because now there are more moles of acid to react, more moles of acid then in the end here to absorb more moles of base or more moles of acid this way. So it's a better buffer. Because there are more moles of acid to react. Okay guys, that is the end of video 5.2.1.